Hi everyone, so today we're kicking off Chapter 9, and Chapter 9, or at least the first half of Chapter 9, is all about exponential growth. And these are things that are growing not by adding constantly, but by multiplying constantly. So that's kind of where this exponential thing comes from. So here is a written out version of what we just said, a definition of an exponential growth function. Exponential growth happens when you increase by multiplication as opposed to addition. So earlier this year, back when we did linear functions, that was back in Chapter 3, we talked about things like, the tree is 4 feet tall right now, and it's going to grow 2 more inches every year. That is growth by addition. But if the tree was doubling in height every year, that would be growth by multiplication. So that's kind of what we're focused on today. Things that grow exponentially grow really, really fast. Okay, so they get bigger really, really fast because they jump by bigger amounts every time you multiply. So an exponential model, this is like the formula for an exponential function always looks like this. Y equals a times b to the power of x. So this might look, when we put some numbers in here, it might look something like this. Y equals 3 times 2 to the power of x. And what this is really saying is that I'm starting with 3 and then I'm multiplying by 2 a bunch of times. Okay? So we refer to, I'm going to get that out of the way here. We refer to this a as the initial value. So that's always going to kind of represent where you're starting. Okay, so A is initial value. And then the B, that represents your growth factor. So that's what you're multiplying by each time. Okay, and the X represents how many times you're multiplying. I'm going to kind of just stick this in parentheses, that this is usually a measurement of time. However, there are situations where it's not time necessarily, it's some other thing that's making you multiply over and over again. But a lot of the times your exponent has to do with time because it's saying, we're going to double every hour or something like that. Okay? So there's all that information again, just kind of written out prettier than what we just had it. Okay? And this down here shows you what one of these would look like if you graphed them. These always have sort of this curved appearance to them. And the one thing I really want you to pick up on is this y-intercept here. Now that one appears to be right at 1, but this value will always match your a value. Okay, so your y-intercept is always at a. It's always at your initial value. So you could kind of say your y-intercept is at 0, a. Okay, and that's always going to be true. Your y-intercept is always going to be at whatever your a value was. There's one other thing we need to know about these graphs, okay? And you'll notice that this curve, it kind of slopes down towards the x-axis, but do you see that it gets like really, really, really close? Okay, like right here, it gets super, super close, but it never actually touches the x-axis, okay? And that is another property of these graphs. They have what's called an asymptote. So the asymptote of a graph, and I know that's a funny word, but the asymptote of a graph is a line that a graph approaches but never touches. It's like an electric fence. Okay, you get really, really close to it, but you would never want to actually touch it. So on this particular graph, and I'm going to grab a different color here, the asymptote is the x-axis, okay? Because that blue line is going to curve really close to that x-axis but never actually touch it. And so the asymptote is the x-axis, and sometimes you're going to be asked for the equation of the asymptote. The equation of the x-axis is just y equals 0. Okay? And this comes from, and we'll get more in depth into this in the days to come, but you can't raise something to a power and have it equal 0. Think about that for a minute. Okay? You can't raise something to a power and have it equal 0. The other thing we want to talk about in terms of the graph is the domain and the range of one of these. Remember that the domain is referring to how far the graph goes from left to right. And really, this graph is a little misleading. It should have arrows on both ends here. So if I go way out here to the right and build a wall that goes on and on forever, eventually my graph's going to hit that wall. And same thing over here to the left, that if I built a wall way out over here, eventually my graph is going to hit that wall. Okay, so I hit everything to the right and everything to the left. That means my domain is all real numbers. And that's true for every one of these exponential functions. And what that's really saying, if I think back to what one of these equations looks like, so like y equals 3 times 2 to the power of x, what I'm really saying there is I'm allowed to put anything in here for x that I want. Okay? Now the range is talking about up and down. So up above my graph, I know that my curve's eventually going to hit, like if I built a wall way up here. Okay, it's eventually going to hit it. But if I build a wall down here, see how this graph kind of slopes and stays above the x-axis? So it's never going to cross over and hit this bottom part of the graph. Okay, it's going to stay above 0 all the time. And so your range for these would be all real numbers greater than 0. And notice I didn't say greater than or equal to 0. I just said greater than, because our graph doesn't actually touch 0. Y equals 0 is our asymptote, which means the graph never actually touches it. Okay, so this question about domain and range, the answer is exactly the same for every one of these graphs. So again, here is kind of all of that information typed up nicely for you if you missed any of it. Any one of these graphs' domain is going to be all reals. The range is always going to be positive reals, which is the same thing as saying up above 0. Okay, so in order to do these problems, you have to understand what's called a growth factor. When you grow by a percentage, you have to be careful about how you're using that percentage. You're not just taking a percentage of the number. You are taking a percentage of the number and then tacking it onto the original. So you're keeping 100% of what you have. So when I say it's increasing by a given percentage, you're always having 100 and then adding on the percentage that you're growing by. So here's what I mean by that. So a 22% increase actually means that I'm taking 100% of what I started with and adding 22 to that. So 100% plus 22% would actually give me 122%. And then what I need to do is make that percentage into a decimal. Okay, so what you know about percentages, we always take the decimal point and move it 2 spaces to the left. So that would mean my growth factor here would be 1.22. Okay, kind of the same thing here, that with 50%, I'm going to do 100% plus the 50%, which really means that at the end I'm going to have 150% of what I started with. And then if I move that to a decimal, again I'm taking my decimal point and moving it 2 to the left, it's going to be 1.5. Now, something like this last one can be a little bit tricky, and I assure you there is no shame in typing this into your calculator if you need to. To do 100 plus 3.8, if you type that into a calculator, it's going to give you 103.8. And then just be conscious about where you're moving your decimal point now. And take that decimal point and move it over 2, and I get 1.038. And that's my growth factor. Okay? So kind of the meaning of this is this, the percent increase, is what's going to be listed in the problem for you. And when you go to set up your equation, this is what goes in for that B value that we had talked about. Okay, so here's our first example, talking about the consumer price index, some economics here for you. And you can see how massively outdated our books are here. So looking at the information given here, the CPI, and you don't necessarily have to understand what the CPI is to be able to do this problem, started with a value of $100, okay? And then between these years, between 1980 and 1990, we're growing by 4.7% per year. And then X is the number of years starting at 1980, okay? And we're going to calculate what would the CPI grow to. So the initial value here, that was my $100. So that's really my A value. Now my growth rate, be careful here. Growth rate was 4.7%, but remember that you have to add that to 100 and change the decimal point. So when you add that to 100 and change the decimal, it should come out to be 1.047. And then time is x. Notice here it says x is the number of years, so we're going to use x to represent our time. Now don't let this mess you up, because I see some people look at this and say, oh, well, the time is 10 years because it's from 1980 and 1990. This is really just telling you that this particular growth factor, this growth factor, was calculated between 1980 and 1990. So if you go past 1990, we're not totally sure that growth rate stays the same. Okay, but we can still use this to sort of make a projection. So when I go to write my equation, I'm going to go back to that formula that we had talked about. Y equals AB to the power of X. And then the initial value is your A, your growth rate is B, and then your time we already have labeled as X. So as an equation, I would write Y equals 100 times 1.047 to the power of X. Okay. Okay. This is still going with that same example, so I'm going to go ahead and write that equation we just came up with up here at the top. So we came up with Y equals 100 times 1.047 to the power of X. Now this very first one is telling me to graph the function, and this is telling me kind of how to set my window. You can go ahead and try that on your calculator, all right? And I suggest that you do try it on your own. Type this equation into your Y equals, and then go to your window and adjust it so that this is your X min and X max and your Y min and Y max. I don't really have a way to demonstrate that here, okay? But we'll go over that in class tomorrow, I'm sure. Then it says, find the CPI in 1985. Well, what we need to remember is that this X doesn't just represent the year. It represents the number of years from when we started. And this equation, this model, started in the year 1980. So that means X would represent 5 years. Okay, because it's been 5 years since 1980. So what I want to do is I want to do 100 times 1.047 to the power of 5. And I'm cheating and using a calculator real quick. Final answer comes out to be 125, and I'm assuming we round this like money, 82. Okay, so I just typed this straight into the normal calculator, not the graphing part, just the normal calculator, and then came out with this as an answer. Now this next question, I'm going to talk about this a little bit, but what I'm really asking is how long before my answer goes over 200, or I'm sorry, I guess not over, but when is it the closest to 250? Now we could do some crazy guess and checking. There is a way to do this with the table on your calculator, but again, let's just plan to go over that piece of it in class tomorrow. Okay, let's hit one more question here, one more example. So the world population in 1985 was 4.9 billion people. Okay, and we're going to double every 35 years. So we're going to write a model to sort of represent what the world's population would be based on how many years have gone by since the starting year, which was 1985. So in this case, my initial value was how many people I started with, and that was 4.9 billion. I think I'm just going to write it as 4.9 and not worry about the billion, and I'll just know that my answer is coming out in billions. Now, my growth rate here is not a percentage, which is different than the other questions we've done so far. If I'm saying that we're going to double, think about what you're multiplying by every time. These are always repeated multiplications. So what am I multiplying by? I'm multiplying by 2. And now your time. This question gets a little bit tricky, but you're going to run into this a lot. If I just put an x, if I just wrote my equation as y equals 4.9 times 2 to the power of x. This x is going to make it so that I double every single year, okay? And I don't want to double every single year. I want to double every 35 years. So I want to somehow take my number of years, which is x, and figure out how many groups of 35 have there been. Maybe this is easier to think about on a smaller scale. So what if I said I was doubling every 4 years, and then I told you 12 years have gone by? Think about how would you figure out how many times have 4 years passed? How many times have you doubled? Hopefully you came up with division. So for your time, it's no longer just x. We're going to take the x, the number of years, and divide by 35, because that's going to put it into groups of 35, which is what this is saying to do. Okay? So my actual equation would look like this. 4.9 times 2 to the power of x over 35. So anytime you have one of these, like an every so many years or every so many hours or whatever, this is how you deal with it up in the exponent. Okay? So now let's take that equation and do something with it. Okay? It says, using this model, what would be an estimate for the world's population in the year 2000? Well, the first thing we need is, what is our x value? And x is years from 1985, so from 1985 to 2000, that's 15 years. Okay, so if I plug that into my equation, I would say y equals 4.9 times 2 to the power of 15 over 35. Now, if your calculator allows you to just type right up in the exponent like this, you can probably type it in exactly as entered. If it does not let you type up in the exponent like this, if you have to, like, if it does one of these, 4.9 times 2 and then to the power of, and then you just keep typing right here, you're going to need parentheses around that 15 over 35. Okay? Either way you go, we should come up with an answer of, let's see, 4.9 times 2 to the power of 15 over 35. I get about 6.6. And notice that's billion. Now, we were told the world's population was going to double. We went from 4.9 to 6.6. That's not doubling, okay? But that's okay because we've only had 15 years go by. It's only supposed to double every 35 years, okay? So it's always good to kind of check back to what you started with and what you ended with and just make sure that your answer seems reasonable. Okay, so something similar here in this next one. What would be the population in the year 1980? Now think about this for a second. If we started in 1985, how do we get back to 1980? Well, I would make my x value a -5. Okay, that's how you would get back to 1980. So I would say y equals 4.9 times 2 to the power of -5 over 35. And think for a minute, what would you expect this answer to come out to be in comparison to the 4.9? Okay? If the population is growing, but we're going back in time, we would expect it to come out to be smaller. So I would say 4.9 times 2 to the power of -5 over 35, and I come out with 4.4. Which again, we did expect it to be smaller, and it was a little bit smaller, but again, we're only talking 5 years, so probably not a huge difference. Okay? Okay, well that's it from me today. We do have some homework to do, and your homework packet should be the very first page in there, and we will spend some time going over this tomorrow, and then tomorrow we're also going to talk about how to do exponential decrease, exponential decay, so how to make things smaller exponentially.